Hello everyone, I am Dhruva Khadka from National Institute for Material Science, Japan. Today I am going to talk about my research work on accelerated degradation of perovskite solar cell under continuous illumination driven by thermal stress. This is outline of my talk. As we know, perovskite solar cell improve device efficiency from 4% to 25.6%. However, device is not as stable as other types of solar cell. So perovskite solar cell has to be stabilized for its commercial application. As we see, device performance with the aging, it degrades with time. If we see the device stability, the material itself is not so stable. It degrades with temperature, with humidity and under light as well. Noting those facts, researchers have improved device stability by encapsulating it and using different electrode layer, using the different STL and ETL layer, and using this approach, the device stability has been improved gradually. However, the device degradation phenomena are not still completely known, and there is much room to understand the device degradation mechanism. To understand the device degradation kinetics, we also prefer device with PTA and nickel oxide as whole transport layer, and this is device with device area 1 centimeter square, and this is the JB characteristic, and we fabricated device of more than 90% efficiency with PTA, and device with nickel spot or nickel oxide has efficiency close to 16%. We use those device for the device degradation analysis, and we place those device under different thermal stress, and by looking this device degradation trend, that is device efficiency trend under different thermal stress, we can see the device with nickel oxide has much better device stability compared to PTA. If we see device efficiency after 1000 hour thermal stress, there is some variation. However, if we compare the device degradation trend, we can notice two stages of device degradation, and this one is exponential decay, and later it follows the linear decay. And we have to explore the degradation kinetics to understand the degradation mechanism, and to have degradation kinetic, we use the Arrhenius model, and we feed the JSC degradation trend of each device under each thermal stress, and then by analyzing Arrhenius plot, we estimated the activation energy of degradation of each device, and we found higher activation energy for degradation for nickel oxide device. This suggests that the nickel oxide has better stability, because higher degradation activation energy is better for stability. And to have more insight, we also perform the post-mortem analysis of those device by analyzing TEM result, and these are the perovskite device with PTA placed under dark, and these are STM image of perovskite device with PTA placed under light and under different thermal stress. We can see this notation corresponds to PBI2 and voids formation and deterioration and ingress at the interface. And we can see the device, the cross-sectional image on the for the device placed under device area placed under light illumination degrade much faster, and it is much more deteriorated, which leads poor device performance with aging. However, if we compare the device with nickel oxide, it is comparatively stable, and of course, if we compare the dark and under light, it has the deterioration rate is much faster, and we can see the interfacial deterioration and bulk formation of lead iodide under higher thermal stress. And of course, the nickel oxide is comparatively stable, and which explain the device degradation trend. And to understand more, we also collected the XRD pattern of perovskite film deposited on PTA and nickel oxide. We can see the perovskite grown on PTA with aging. It increased the PBI to peak, which suggests that with the perovskite film on PTA deposited on PTA layer degrade much faster, and then which also support the faster degradation trend of PTA device. Actually, PTA itself is denatured when it is exposed under light and under heat with aging. That's why it also accelerates the deterioration of bulk. Moreover, we also collected the XPS spectra of different ETL and STL layer, that is PTA, nickel oxide, and PCBM placed under different ambient condition, iron rich or Ma rich, Ma vapor rich condition. And of course, this plot here, this slide is very busy, and just to have some of if we see the PTA layer, and PTA layer degrade faster with iodine interaction. However, although there is some formation of very thin layer of nickel iodide and some change in surface ionic state, oxidation state, but it still retains the its property rather than deterioration as like PTA, and that's why device with nickel oxide is comparatively stable. And to have more insight on the optoelectronics characteristic of a degraded device, we compare the capacitance spectra of nickel oxide and PTA device, and we compare the phase under dark and under light, and we can see this deterioration of intrinsic property for device with PTA. However, nickel oxide device retained its intrinsic property, and we can see the hysteresis at higher temperature and under illumination. This could be due to deterioration of interface with ionic or charge carrier accumulation at the interface. Moreover, we also compare the carrier profile by analyzing CV characteristic. We can see there is widening of interfacial width, and it has been this compared to fresh one, it is shifted from 80 to 120 nanometer. However, the shifting of carrier profile is much lower for nickel oxide, although there is no significant change in carrier profile in the bulk, but there is some little bit fluctuation in the carrier distribution at the interface, that range in the range of 10 to the power 2 to 5 10 to the power 18 with aging. and then we also reproduce those characteristics with simulation using the scafs, and we varied interfacial defect layer density and interfacial defect layer thickness, and it follows those trend, and somehow it explains our result that interfacial layer widening of interfacial defective layer is one of the cause for the device deterioration. In sum up, we analyzed the operational stability of perovskite solar cell under thermal stress and performed the post-mortem analysis. We found the degradation of perovskite solar cell is caused by interfacial deterioration and bulk decomposition, and it is led by the cracking of columnar intergrain and defective spot in perovskite bulk with the release of iodine gas, and the degradation is also affected by nature of HTL layer. To have remedy for degradation of perovskite solar cell, we have to passivate the columnar intergrain defect in the perovskite bulk. Also, we have to laminate the interface with chemically inert layer. Finally, I would like to thank our research team, and I am also thankful to Yazaki and Kurata Foundation for research support. Thank you for hearing my presentation.